Compound interest is interest that is paid on both the original principal and the accumulated interest. Now, this interest could compound after many different time intervals. And we'll do some examples describing what I mean by that. So this first one, suppose you deposit $1,000 at a 10% annual rate compounded annually. How much is in the account after 3 years? So what that means compounded annually is you figure out how much interest you earn in 1 year, and then in the next year, the interest will be the interest that you earn on the original plus that first year of interest. So let's write this like this. So let's say after 1 year, because this is an annual rate compounded annually. So after 1 year, we will use the simple interest computations to find the interest earned. So let's say after 1 year, interest earned is what? Well, what's the interest earned? You deposit $1,000 and it earns 10% in a year. 10% again is 0.1. So the interest earned is $100 after the first year. And then also we're still under our after 1 year, and the amount in the account after 1 year is $1,000 plus the 100 in interest, which is $1,100. Well, that's great. What about after 2 years? Well, let's again find the interest earned and then add it to the 1,100 that you had beginning of year 2. Interest earned is, now this is compound interest. So the interest is going to accumulate on the original 1,000 plus the 100 of interest from year 1. So at the beginning of year 2, you have $1,100, and it earns interest still at 10%. The interest rate isn't going to change in the next year. It's still 10%, but it's earning on $1,100 this time. So right there in year 2, you earn $110. And the amount, let's put bullets here. Bullet after year 1, bullet after year 2. And the amount in the account is, where are we? 1,100 plus 110. And what does that equal? 1210. Gee, have we seen 121 before? I don't know. Well, yeah, I do know. Let's look at what happens after year 3. Because this question says how much is in the account after 3 years. You don't want to just stop after 2 years, because then you won't get full credit. We all want full credit. So after 3 years, interest earned is, what's the interest earned? Well, at the beginning of year 3, this is compound interest, you have $1,210. It earns at a rate, again, of 10%. 10% of 1210 is 121. So the interest earned in year 3 is 121. So the amount in the account is, where are we? We started with 1210. We want to add the interest. 1210 we start with plus the interest 121 gives us, what does it give us? It gives us 1331, and our units are dollars. Now I know I've seen 1331 before. So how much is in the account after 3 years? $1,331, as opposed to simple interest, where with these numbers you would have $1,300. So as a side observation, where have we seen these numbers before? Let's ignore zeros. 100. Well, no, actually, let's ignore zeros. At the beginning you have 1,000, 1,100, 1210, 1331. Ignoring zeros, 1, 1, 1, 121, 1331. Have we seen that before? Yes. In Pascal's triangle. Now, why is that showing up here? Well, it shows up here because of the 11 times tables, actually. Because 11 squared is 121, 11 cubed. Or no, yeah, okay, 11 cubed is 1331. But the reason these numbers shows up could actually be interpreted using Pascal's triangle, that same type of adding argument. But you don't need to know that here. That was just a connection between this week and, what was that, 2 weeks ago? Let's do another example. And to do this example, I'm just going to change these numbers around. Suppose you deposit $1,000 at 10% annual rate, but instead of compounding annually, let's compound it quarterly. Compounded quarterly. How much is in the account? And let's do after 1 year. Doing 1 year here, we'll illustrate what we need to illustrate here. So here, how much is, well, here the interest is compounded quarterly. That means something. But then how much interest, how much is in the account after a year? That's similar to what we're doing. So what we need to do first is interpret this compounding quarterly. Compounding quarterly just means that you're going to earn interest 4 times a year. So after 3 months you'll earn some interest, after the next 3 months you'll earn some interest, after the next 3 months you'll earn some interest, and then at the end of the year you'll earn some interest. So each quarter you get some interest. And after that quarter is over, the interest you earn, you then earn more interest on, because it is compounding interest. So let's set it up like we did over here. After 1 quarter, because we're compounding quarterly, after 1 quarter, interest earned is what? How do we find the interest that's earned in 1 quarter? Well, what we need to do, we started with our $1,000. Let's write this a little larger. We started with $1,000, but how much interest is earned in 1 quarter? How could we figure that out? Well, it's 10% in a year. But our units up here aren't years anymore. Our units up here are quarters. How many quarters are there in a year? Well, a quarter is a quarter of a year. So we'll remark down here. Maybe I'll remark over here. Will I have room down here? I'm going to write the remark here, but then I'm going to erase it. So, remark. So I'm going to do the computations like we did before, where we have, in this case, we're going to have 4 after 1 quarter, after 2 quarters, and so on. So this remark you might want to put by this question, or leave some space and put it after 1 quarter, after 2 quarters, and so on. So remark. It's compounded 4 times per year. That's what compounding quarterly means. And at a rate, not at a rate of 10% per year. So the interest paid each quarter, or the interest rate for each quarter, so the quarterly interest rate is 10% divided into 4 pieces, which is 2.5%. percent. So given an annual rate, we can find a quarterly rate by just dividing it into 4 pieces. If interest were compounded semi-annually, that means twice a year in interest language. If interest were accumulated, or if your deposit were compounded semi-annually, the semi-annual interest rate would be that rate divided by 2. If it's compounded monthly, it would be that rate divided by 12, and so on. So here in 1 quarter, it's going to earn 2.5%, which is 0.025. So after 1 quarter, the interest earned is that times 0.025, which is $25, and this is the same as that because you move this decimal place over twice and you get 2.5. So after 1 quarter, you earn $25, and the amount in the account is what? 1,000 plus 25, so $1,025. So here we played with the rate. And now I'm going to erase it because this is going to be the same rate for each quarter. And overall, that does add to 10% for a year. So let's do after 2 quarters. Interest earned is what? Well, at the beginning of quarter 2, you have $1,025. And it's again at a 2.5% rate. So 1,025 times 0.025 is 25, it's approximately 25.6. It's actually 25.625, but we will round that up because 0.625 rounds up to 63 cents. So the amount in the account is 1,025 plus 25, 63 equals $1,050.63. Well, okay, so that's after 2 quarters. What about 3 quarters? After 3 quarters, the amount in the account is, so here I'm just going to jump straight to the amount in the account. Well, we start with $1,050.63. But then we have to add on the interest earned during quarter 3. So the interest earned is still going to be that times the quarterly rate. Point, that's not a 0. 0.025. So the interest earned in 3 quarters is that amount, 1,050.63 times 0.025, and then the amount in the account is the interest plus the original, and that adds to, where are we? 1,076 and I can't read my numbers. 90, and that's an approximate too. Okay, great. That still didn't answer what we want. We want what happens after 4 quarters, which is 1 year. After 4 quarters, the amount in the account is what? Well, it's the amount at the beginning, 1,076.90 plus the interest earned. So at the beginning you have 1,076.90, and then you earn interest at a 2.5% rate per quarter. So that times 0.025, and that equals an approximate $1,103 and I think it was 82. Yeah, it was 82. 82 cents. So right here, compounding quarterly means it compounds after each quarter, and you have to divide your year into 4 pieces. So in this case, the answer would be this number. This was a textbook question, and I had to take this question, and it's appropriate that we have it this week. 1,103 and 82 cents. My birthday happens to be 11/3, which is Tuesday of this week. However, I was not born in 1982. I'm 1991, which is not 1982. So it's off by 9 years, but I guess that's okay. Let's define this rate a little more formally. So here we had this rate, and then we had to deal with breaking it into the time blocks that we need for the question that we have. So let's define a couple words. Remark. The periodic rate, so the rate for a given period, we're going to define it to be I, and it equals, so the periodic rate equals I, and it equals the given rate divided by M, where, let's erase some of this because this is going to go over here. Which equals the annual interest rate divided by the number of compounding periods per year. So here, just to define these rates a little more formally, you're going to be given, for the most part, an annual interest rate. For these compounding questions, I believe I will stick with annual rates, just because if I don't, changing the rate from annual to something else introduces unnecessary complications. And the complications I would like to introduce are more illustrative than that type of complication. So I will, for compounding interest, stick with an annual rate that you have to deal with. Like in that last example, we had to deal with compounding quarterly. So we had to divide the annual rate by 4 to figure out the rate for the given period. So remark, this is actually a remark and a definition. So let's just leave it as a remark. The periodic rate I is the annual rate divided by the number of compounding periods per year. So we had, for simple interest, we had a simple interest formula. Is there a corresponding compound interest formula? Yes, there is. And let's, before writing it down, let's derive it. And we're going to derive it following the reasoning in the previous example. So there are going to be two formulas which look different, but actually say the same exact thing, depending on the units you're given. And because I will generally always give you an annual interest rate, the second formula is the one we will use. But for the derivation, I will derive the first one, and then the second one will be the first one with some different letters. So how do I want to write this? So suppose you have P, a principal amount that you invest. Suppose it has, so P is principal. Let's let I be the rate. So it's the periodic rate. So that's all we're going to need to derive this formula. Well, actually, it's not. So let's see how it goes. So the periodic rate means it's a rate for a given time period. So let's say after one time period. After one time period, what is in the account? Remember, the simple interest formula gave us the amount in the account. So in the compound interest formula, we're going with the same thing. So after one time period, how much interest is earned? Well, after one time period, the principal times I interest is earned. Well, that together with the principal amount gives you the amount in the account after one time period. And here, I will tell you that factoring this will be helpful. So we'll pull out a p from both terms. You're left with a 1 plus an I. Now what happens after two time periods? After two time periods, well, the same thing happens. You start with an amount. In this case, remember, that p times 1 plus I is the amount in the account after one time period. So at the beginning of time period 2, that's what's in the account. And that's the amount we're going to earn interest on. How much interest? Well, it's at a rate of I. Notice our units are the same because the rate I is in whatever time period, and here we're saying these units are also time period. We have p times 1 plus I plus p times 1 plus I times I. That looks complicated. Is there something we can do with this? Yes, there is. Where do I want to write this? Let's write it here. Where should I write it? Let's write it here. We have two terms. We have those two terms. Do they share anything in common? Yes, they share a lot in common. They share a p. They share a 1 plus I. So we can factor out a p times 1 plus I from both of these terms. If we do that, what are we left with? We factor out a p times 1 plus I from this. Well, that takes everything away from it. So we're left with a 1. If we take a p and a 1 plus I away from this, we're left with only I. So we have p times 1 plus I times 1 plus I. Well, p times 1 plus I times 1 plus I can be resaid more succinctly. Because 1 plus I times itself is 1 plus I squared. That looks a lot like this. What happens after a third time period? So after 3 time periods. Well, maybe I should move that a little lower. Now I'll just put it under here. After 3 time periods, what do we have in the account? Well, this is the amount after 2 time periods. So that's what we start with. P times 1 plus I squared. Plus, we earn interest on that. P times 1 plus I squared times the rate I. So all of these first equations we wrote are initial amount plus a new amount. This is initial amount plus a new amount. This is initial amount plus a new amount. Or well, maybe I should say initial amount plus interest earned. Initial amount plus interest earned. Initial amount plus interest earned. And is there something we can do with this? Well, yes, there is. Because this term and this term, again, share a lot in common. They share a p. They share a 1 plus I. They share another 1 plus I. So we can pull off a p, we can pull off a 1 plus I, and we can pull off a second 1 plus I. So we can pull off a p and a 1 plus I squared. If you take that away from here, you're left with 1. If you take that away from here, well, that gets rid of the p, that gets rid of that 1 plus I squared, and all you have left is an I. So 1 plus I, and of course, 1 plus I squared times a third 1 plus I gives us p times 1 plus I cubed. And right now you can see the amount you earn, or the amount in the account after a certain number of time periods. That number of time periods is going to show up in our formula as an exponent. So let's write this as one formula. So our first compound interest formula is the general compound interest formula that we just derived. An initial principal P in an account that pays interest at a periodic rate I grows after n compounding periods to that quantity, P times 1 plus I to the n. And we saw that for I equals 1, 2, and 3 before. Now, the rates we're going to deal with are going to be annual rates, and you could use them to figure out I and n. It's sometimes more convenient to actually introduce a couple additional variables in finding compound interest. So this compound interest formula 2 is the same as 1, but it assumes an annual rate instead. And with an annual rate, we're also going to want to know the number of times it's compounded per year. So initial principal P, the period is just meaning the same words as over here. The initial principal P in an account that pays interest at annual rate R, remember as a decimal, compounded m times per year, grows after t years to that amount. So the rate, of course, is the rate, or I here, remember, is R over m from the previous remark. But then the exponent, up here we just have n compounding periods. Mt gives the number of compounding periods because it's compounded m times per year, multiplied by year, year cancel, and you're left with the number of times it's compounded. So in these next couple examples, we will use that formula instead of the more general formula, because our rates are going to be annual. So, example. Suppose you have or deposit $1,000 with annual interest rate. What do we have? 10%. And the question will be, determine, am I going to ask another question after these four? No, I'm not. So determine the amount in the account after 10 years given 4 parts. A, annual compounding. B, quarterly compounding. Is this the one we did before? Yeah, I guess it is. Oh, no, this is after 10 years, so it is different than the one we did before. Compounding. C, monthly compounding. And D, daily compounding. So we have 4 questions here. Suppose you deposit $1,000 annual interest rate 10%. Determine the amount in the account after 10 years, given annual compounding, quarterly compounding, monthly compounding, daily compounding. Well, we're just going to use this formula. We just have to be careful that we use it properly. So R is the rate. Well, I guess P is given first. P is the principal. P is $1,000. That's a T up there. So let's call it A in each case. So I'm going to just answer these going straight across the board. So for part A, for annual compounding, we have A equals P, which is 1,000, times 1 plus R over M. What's R? Well, for that formula, we assume an annual interest rate, which is what we have. So R is 0.1. 10% is 0.1. Divided by M. M is the number of compounding periods per year. Did I write per year? Yes, I believe I did. Yes, I did. This is still showing. M is the number of compounding periods per year. How many compounding periods are there in 1 year with annual compounding? That's right, 1. That's wrong if you did not say 1. If it's compounding annually, then it compounds only once at the end of the year. Well, interest accumulates only once at the end of the year, I should say. So we have M equals 1. So then it's raised to the 1 times T, which is 10 years. That's a lot of ones. So 1,000 times 1 plus 0.1 to the 10 is approximately, well, actually, for these first two, I'm actually going to simplify. Yeah, I guess I will simplify the first two, and now I won't. This is approximately $2,593.74. I was going to write that this simplifies in the middle to 1.1 to the 10th. So this equals 1,000 times 1.1 to the 10th. I'm not going to write that. I'll just do the calculation. For these calculations, yes, you are allowed to use a calculator. When I say you're not allowed to use a calculator, it's not because I want you to go through a computation like this. It's because I don't want you to use a calculator for things like 6 times 4 and 100 divided by 10 and things like that. But for things like this, yeah, they are okay, obviously. Just rewriting the formula there. Okay, quarterly compounding. Well, P, R, and T are the same. So A still equals 1,000 times 1 plus the rate is 0.1. This formula, for any of these, that formula assumes R is 0.1. It assumes R is annual. Quarterly compounding means it's compounded 4 times a year, which means M equals 4. And I'm going to have to write smaller. Well, that's okay. So M equals 4, T still equals 10, and we get what? $2,685.06. Well, that's great. We did 2 of them. How about monthly compounding? How many months are there in a year? Well, we already discussed that unit conversion on this board. 1 plus same rate divided 12 times in a year. So M equals 12. So here we have 1,000 times 1 plus 0.1 divided by 12 to the, in this case, 120th, which is approximately $2,707.04. Now, how about daily compounding? We will not worry about leap year. This year is, what year is it? 2020. This is a leap year. Who knows the rules for when a leap year occurs? For interest, we will not worry about leap years. We'll just assume exactly 365 days in a year. So that tells us M is 365. So m is 365, p is still 1,000, r is still 0.1, t is still 10, and that equals, where are we, $2,717.91. So who knows the who knows the rules for a leap year? Well, actually, before discussing the rules for a leap year, let's just take a look at these numbers for a moment. Look how close the last two numbers are compared to the first two numbers. The first one says it's compounded once a year. And in 10 years, well, great, it turns into that. But if it compounds 4 times in a year, look at that. You earn almost an extra $100. You earn what, $92.78 more? No, I'm off by something. You earn God, I can't do math in my head anymore. $91.32 just from compounding quarterly. Now, compounding quarterly means it's compounded 4 times a year. Compounded annually, compounded once a year. Compounded monthly, 12 times a year. But going from 4 to 12 earned you only $22 extra, $21.98. And look at what happened going from monthly to daily. Daily is compounded 365 times in a year. And going from compounding 12 times a year to compounding 365 days a year earns you only $10 extra. Look at this gap. That might make you think that there is a limit to how much you can divide a year up. Well, to how much money you can earn based on how much you're chopping a year up. And there is, and we'll see that in a moment. But not yet. So who knows the real rules for leap year? You said, what? A leap year occurs once every 4 years. And in our case, a leap year occurs in every year, which is a multiple of 4. You are wrong. What? Yes, wrong. I learned in, I guess it was my second year of undergrad, maybe my third, I think it was my second year. My second year of undergrad, that is not the actual standard for a leap year. A leap year occurs every 4 years, except for years which are multiples of 100, 200, and 300, but it does occur for years which are multiples of 400. So what does that mean? It occurs whenever you just fought every year that with a multiple of 4. It occurs in a year 2000, which just happened. There is a leap year. 2000 multiple of 400. 2100, yes, that's a multiple of 4. It's 4 times what, 525? But no. There's no leap year in 2100. 2200. There is no leap year in 2200. 2300. There's no leap year in 2300. 2400. There is a leap year. Maybe I'll put an exclamation point there too. Leap year occurs in a year which is a multiple of 400, but it does not occur in a year which is a multiple of 100, but not a multiple of 400. And then, of course, every 4 years other than these, it does occur. If anybody knew that, I'd be actually surprised. How did the reason I figured that out is because someone was asking me, oh, what day is so-and-so in a certain year, and I got one of them wrong because it was after year 2100, and I forgot to factor in the leap year for that year, or the lack of a leap year for that year, because I didn't know about it. So I maybe some of you did know that. That's I was not taught that in school. But you are all taught that in school if you're watching this video. So that's good. Back to investing, much more interesting than leap years. Suppose let's just do one more example like this, have $5,000 invested. I shouldn't say invested. I mean, this could apply to investments, but I'm not going to use the word investment. I mean, all this interest rate stuff you could just translate over to investment and how much you earn on it, but let's just stick to deposit. Suppose you deposit $5,000 at an annual interest rate of, so at an annual interest rate of 1.41%. 1.41%. How much is in the account after 2 months with, oh no, I changed that to a 7. After 7 months, I didn't want the fraction to reduce. After 7 months with monthly compounding. So let's reread this question, make sure I wrote it right. Suppose you deposit $5,000, annual interest rate 1.41%. How much is in the account after 7 months with monthly compounding? And I did not write that correctly because I need a question mark. Well, we're going to follow the same formula. What was it? P? No, it was A. It was A equals P times 1 plus R over M to the MT. That's an M. So in this case, we start with $1,000. $5,000, excuse me, times 1 plus the rate, 1.41%. Be careful with all these ones all over the place. .41% as a decimal is 0.0141. Divided by M. M is what? The compounding what? So this up here is an annual interest rate. M tells you how many times it's compounded given an annual interest rate. So how many times it's compounded in a year. In this case, M equals 12. So that also gives us a 12 up there. And we have 7 months. And we have 7 months. What is currently written is incorrect. Why is it incorrect? Well, we have to go back to our units. With this formula, with the M's and P's and R's and T's, we want everything to be in years. And 7 months is not in years, so we need to convert that to years. 7 months, we want to convert to years. So we have years and months. There are 12 months in a year. So that gives us 7/12 of a year. So we have 12 times the number of years, which is 7/12. And this number is approximately equal to $5,041.27. And that answer does make sense because it's only 2 months. You throw 5,000 in at a relatively low interest rate, so you wouldn't expect this to be much higher. These interest rates we're using in these examples, even this last one, very unrealistic for savings accounts right now. Savings accounts are earning like nothing. They are barely worth having. And well, maybe I shouldn't say what mine is, because that would suggest to you how much money I might have, and that's probably supposed to not be public. But, you know, it's like a few pennies every month. It took me a while to remember what my how frequently they give interest. I mean, it's a few pennies a month. You barely notice a few pennies a month. Now, these two interest rates, these two methods of accumulating interest, the compound interest and the simple interest. On page 876, there's a chart with an example comparing the simple and compound interest growth for many different time periods. And I'll just tell you in a graph what they look like, but it might be a good idea to look at the chart on page 876. I think it's the bottom of 876, just to see how much more you'll earn with compounding interest. But in general, simple interest grows as a line. It is a form of arithmetic growth. So it's like $100 each time period, and that'll define a line because it'll give you a slope. Compounding interest grows exponentially. And you can see that because we have exponents all over our, we have variables in exponents in all of our compounding interest formulas. So let's say that's compounding, and this is simple interest. So compounding interest grows exponentially. Simple grows linearly. Simple is a form of arithmetic growth. Compounding is a form of geometric growth. I'm not going to ask you about those words. They're just words. But let's look at one other thing. I like the word thing. It's a very useful word. Well, let me give you some numbers first.